Okay, I'll just be presenting from good afternoon. Thank you everyone for coming. My name is Kristen Frederick. Today I'll be talking about the geology, volumetrics, and prospectivity of Miocene turbidite reservoirs in the King area of Mars Field, Gulf of Mexico. So the story I'm going to be telling you today is an analysis of a new data set which shows expanded reserves or expanded resources and possible exploration potential. Okay, so just a brief outline of what I'll be talking about. I'll go over the objectives of my project and some challenges that I faced, and then I'll take you through geologic background and some of the well history. And then I'll take you through a step-by-step analysis of all the work that I did with a few examples and some of the highlights. And then we'll wrap up with a quick summary. Okay, so the objective of my project was to utilize the new Ocean Bottom Seismometer, or OBS, merged seismic data set to look at geology, volumetrics, and prospectivity for the King area. So just to give you some reference, okay, here is the city of New Orleans, and right here is the Mars Basin. So starting with my workflow, I interpreted shallow and then deeper horizons. From there, I generated structure and amplitude maps in Shell's interpretation software, NDI. I imported all of that in Petrel and used Petrel to build net sand and connected area scenarios, a minimum, most likely, and a maximum, and I'll talk about that in just a bit. And then lastly, I built in-place and recoverable volume distributions for each of the units with a focus on key uncertainties. Okay, so a few of the technical challenges I faced was some complexity in recognizing geologic features in both the seismic data and also in map view. This was a bit of a personal learning curve. I also found some of the reservoirs difficult to identify, particularly the deeper units where the data set had low resolution. Also, it was hard to estimate net sand thickness because there's only one well located within my area. Okay, and that well is the 764, and I'll be talking about the history of that well right now. So the 764 lease was awarded in '87. It was drilled by Shell and BP in '97. The conservation information document, basically the plan, was approved in '99 and included commitments in the yellow, magenta, and violet. So this well log over here highlights those sands. The yellow on the left indicates that it's a sand, and the green on the right indicates that there's pay or oil. The reservoirs in the King area are named after colors. That's the magenta, violet, and the yellow. For confidentiality purposes, I will be referring to these later using arbitrary numbers. So the first oil in yellow sand came about in January of 2001, and they built a subsea tieback to the Mars A platform. So here on this diagram is the Mars A tension leg platform. Over here is the MC764 well, and this is just a series of pipe running along the ocean floor back to the platform. Okay. Shell's initial interest in the King area was 33%. In 2010, a commercialization agreement between Shell and BP occurred, and they agreed to equalize their well interest. So that's what you're seeing here on this map, shaded in red is the equalized well interest. Here is the King extension and the 764 lease block. To the west is West Glorious and South Deimos extension. To the east is Ursa, that's kind of off the map, and then Crosby, another neighboring field, is kind of way down here. So in the middle here is the Mars A platform location and the potential location of the Mars B platform. These are outlined by a blue line, which is the salt suture, which I'll talk about a little bit more later. But you can see that the Antares salt is located in the north and west, and the Venus salt is located in the south, and they bound the Mars Basin. Okay. In 2010, the yellow sand failed, and the plan was updated to exclude magenta and recomplete to the violet. The yellow and magenta are currently within the Mars A and B development, but no other plans have been made. And there is possible exploration potential that exists on the 764 lease block. So the focus of my project is to answer the following questions. Is this the scope of future development? And what can the OBS merge dataset tell us? Key stakeholders for my project include both Mars and Ursa assets, as well as exploration at Shell. Okay, now we'll move to talk about the geologic setting. So the Gulf of Mexico, Mars Basin is a typical deep water Gulf of Mexico salt withdrawal basin. So here I've labeled this as a salt body. We know it's salt because it has a chaotic seismic signature. We have shallow Mars here, which is a bypass phase deposited during the lower Pliocene to the upper Miocene. Deep Mars is located here. It's a ponded intra-slope salt basin deposited during the upper Miocene. And then we have Deimos and West Boreas neighboring fields. I'm going to explain what all of that means in just a bit. But let's start by talking about what a turbidite is. A turbidite is a sea bottom deposit that's formed by a massive slope failure, typically where large deltas have been deposited. They're usually triggered by sediment loading or sometimes earthquakes. So in this diagram here, we have the delta, which is depositing sediment. As sediment piles up, it begins to load and creates these slope failures. So these turbidity currents travel kind of crazy like down and then settle. So they're coming down this canyon, scouring out channels, and then they deposit finger-like lobes, one on top of the other. So here you can see, this is kind of what it looks like at the surface, and you can see a little bit that there's a scour here from the channel, and then that's what it looks like today. Okay, this is a schematic explaining it's a typical deep water Gulf of Mexico salt withdrawal basin. So the deeper section of Mars is this ponded intraslope, the Tanner section here. So as sediment is being loaded, it pushes down and allows the salt to evacuate up. As evacuation happens, it builds accommodation, and these turbidite sheet sands are being deposited, filling the basin. When evacuation slows, accommodation lessens, and the fill character transitions from this ponded intraslope to our bypass phase, and that is the shallow portion of the Mars Basin. Okay, like I said, Mars is an intraslope mini basin. It's bounded to the north and west by the Antares Salt and to the south by the Venus Salt. These are remnant of the Luan Salt, which was deposited during the Jurassic and then reactivated due to sediment loading. As this salt evolved, it formed a suture between the Antares and the Venus Salt, which encircles the entire Mars Basin. So the Pliocene and Miocene turbidites that are deposited in this basin came from atop salt highs, traveled down through narrow entryways between salt bodies, and were deposited along these amalgamated channels. The deep basin of Mars is filled with laterally continuous turbidite sheet sand. The shallow portion has more scour and erosion. Okay, so this is a look at the salt suture that I was talking about. So to the north is the Antares Salt here. You can see it has the same seismic character as the salt body I showed before. Here is the Venus Salt, and between these are all 15 horizons that I interpreted in the basin. So down at the bottom, this white line is just to indicate where we are in space. And you can see here's the Antares Salt to the north and west, the Venus Salt on the bottom, and the King extensions were coming right along in here. This map shows the aerial extent of my project. So the larger white line indicates the total area that I mapped to. You'll notice this red box here. This is a 764 lease block with all these polygons overlaid on top of each other. This is to show that our focus is within the 764 lease block, and those polygons represent the connected area scenarios. I'll explain more about what that is in just a bit. To the left, we have West Boreas and Deimos, King, Ursa, and then Princess, which is a sub-basin of Ursa, and then Crosby way down here. Okay, look at the data set. It's a negative 90 degree phase shift, or quadrature. This was chosen because it better represents the geology. It's a little more easier for interpretation. The frequency content is 25 hertz. The OAS merge data contains or combines the Deimos, the Mars, and the Queen Ursa Oasis extension data sets. And it also uses an Ursa Princess Crosby, or UPC velocity model that incorporates the Deimos velocity model as well. Velocity model is just the way that they process the data. So here's, again, another look at all that I've interpreted and where we are in space. Okay, there were some issues with the quality of the seismic data. Overall, this data set was of lower resolution than some of the previously interpreted data sets. This was particularly concerning for our more continuous reservoirs, such as the 5 and the 7. Also, looking at some of the deeper exploration was particularly chaotic, especially against the salt. Okay, this is another example of interpreting along the salt. There's salt to the left, salt to the right, and you can see that these, particularly the deeper layers, there's a lot of discontinuity, can't really be carried across the basin with confidence. So I think that it's possible that there may be some other data sets with maybe a wider azimuth angle that might help with some of the interpretation for these subsalt reservoirs. We'll talk about that in a bit. Okay, now I'll take you through a step-by-step analysis of all the work that I did. I'm going to use Reservoir 1 as an example. So I started by interpreting a seismic horizon, and I created the structure map and extracted the amplitudes. So that is shown here. So the warmer colors indicate brighter amplitudes, possibly the presence of hydrocarbons. Cooler colors indicate a lower amplitude, possibly water. So from there, I created net sand maps using thicknesses from well data, trending to the amplitude, and some geologic modeling. So this in the middle here is a well log. The yellow indicates that there's a sand. The blue indicates that there's water. So for Reservoir 1, we have 22 total vertical net feet of wet sand. And this is the net sand map here at the bottom. Even though I've mapped this entire area, the focus of my project is really within this red box right here. Okay, I also performed a volumetrics analysis for each reservoir. So I'll just take a second to pause, and we're going to talk a little bit about what goes into the volumetrics. So we look at net sand thicknesses from the well logs and choose polygons for our net acre feet. Those multiplied together to give us a volume, and then we also assess reservoir characteristics such as water saturation, porosity, permeability. So for the volumetrics analysis, each of the volumes were weighted based on a minimum, medium, and maximum scenario. Also, a recovery factor was applied to each of those. So 3 recovery factors per scenario. That gives us 9 total possibilities for each reservoir. So there are 3 types of recovery factors, and these numbers are based on analog data from nearby fields such as Deimos, West Boreas. First is aquifer support, about a 40% recovery factor if there's some aquifer support, typically 50 to 60% recovery if there's good, strong water support. The second type is typical compaction expansion drive, and that's usually between 25 and 30% recovery, with 30% being your depletion drive, which is maintains the pressure from a gas cap. The third is about a 20% recovery, and that's to account for smaller scale heterogeneities that could affect the recovery. So for Reservoir 1, you can see there's a little kind of a white outline of our maximum case scenario here. The well is this red dot here, and we have a lot of cooler amplitudes. So because of the elongated shape of this reservoir combined with what we believe is a large aquifer down dip is most likely to result in coning near the well, meaning we would produce water instead of oil. Okay. This is a recoverable volume distribution. I created these for all the reservoirs. This is the example for reservoir 1. So on the bottom we have recovery in on the x-axis we have recovery in millions of barrels oil equivalent. This is the estimated ultimate recovery. On the y-axis is the cumulative probability. So each of the red dots on this chart represents one of the 9 scenarios that I talked about. So from this data, we create a best fit line, and that helps us determine our probabilities. So the P90 in this case represents a 10% chance of success. The P50 represents 50%, and the P10 represents 90%. So at our P10, we have a 90% chance of finding 12.5 million barrels of oil equivalent or smaller. Okay, now I'm going to take you through some of the highlights. So there was particular interest in Reservoir 5. Previous interpretations had it mapped to closure at the West Antares. You can see that there's cooler amplitudes along this structure here. The new data set shows that Reservoir 5 continues further to the east with brighter amplitudes, and they have a fit to structure, so they follow the contour lines. And you can see that here, these bright amplitudes fit along the contour. So the implication is that the volume for Reservoir 5 extends beyond the King area, and that there's possibly a potential connection to Ursa, which would be somewhere over here on the map, via the oil column. So this could tell us a lot about our production and our reservoir characteristics. Oops. Okay. We also see a similar observation for Reservoir 7. So you can see not a lot of bright amplitudes for the initial interpretation for previous data sets, but the new data set shows brighter amplitudes here along contour, and then quite a bit of extension off to the east there. Okay. Another aspect of this analysis was looking at some of the lower resolution data sets. So the deeper reservoirs, the unexplored, was Reservoir 10 through Reservoir 15. So because of the low resolution data set, there were some reservoirs that looked separate in certain views and then combined in other views. So you can kind of see that here in this seismic section where you have some discontinuities. It looks like 10 continues, but maybe not. And then 11 kind of breaks off, but maybe not over here. They combine. And so that was the first clue that these Reservoir 10 and 11 might be one continuous sand. The second clue is to look at the amplitude maps, the structure maps. So in Reservoir 10, we see a little bit warmer color or warmer amplitudes in the eastern section, but almost nothing in the in the western section, almost nothing in the northeast. But in 11, we see the opposite. So this indicates that they're most likely one continuous sand. It's also possible that we have aquifer support in this area. We know that because if you look at this well log, this is a 764 well for 10, Reservoir 10. The yellow on the left indicates that there's sand. The blue in the middle indicates that there's water. So we have 60 total vertical net feet of wet sand. We also see this in event 11 in this amplitude map, where we have the really bright amplitudes up here in the attic, meaning it's at higher elevation above the water. And there's almost no amplitude here, so this could indicate that we have a large aquifer down dip. I'd also like to point out that you might notice there are 2 polygons here, one white polygon just surrounding the really bright amplitudes, and then another polygon with a fit to the contour. So this was a comparison that I did for the volumetrics. The first is honoring specifically the amplitude. The second polygon looks at more of a geologic interpretation with a fit to contour. So for Reservoir 10, it looked at a comparison of those 2 scenarios with a fit to total closure versus honoring explicitly the seismic amplitude. For this analysis, I varied the sand thicknesses, and they were weighted independent from the acreage. Also, the recovery factors, there were only 2 based on either the existence or not of aquifer support. So the results of this was that the most likely scenario is that reservoir 10 and 11 are one continuous sand supported by an aquifer. Okay, these are the results of my volumetrics analysis. This is a preliminary results. So the total most likely recoverable volume was 28 million barrels equivalent. The total expected recoverable volume was 83 million barrels equivalent. Exploration potential below reservoir 10, so 10 through 15, was not adequately assessed due to chaotic nature of seismic data. So to account for that, I applied a probability of success to reservoirs 10 through 15 by weighting the reservoir charge and trap for each. So to summarize, the new OBS merge data set did provide new insights, particularly in the eastern extension of reservoir 5 and 7. I also assessed that there is some shallower potential for reservoirs 1 and 2. Like I said, nothing below 10 nothing below reservoir 10 was adequately assessed due to chaotic nature of the seismic. And the most likely volume was 28 million barrels equivalent with a significant upside. So some future work that I'd like to do on this project is to look at other data sets that may have improved resolution in the deeper units. I mentioned possibly one with a wider azimuth to get a better look at those subsalt reservoirs. I'd also like to map the same units using just the DEMOS velocity model and compare those to the UPC velocity model to see if there's any improvement in the seismic data. I would build detailed net sand maps for every unit and edit my minimum, medium, maximum scenarios to fit to closure rather than just on amplitudes, because we've seen that makes more geologic sense. And of course, I'd need to revise my volumetrics. I'd also like to incorporate well data from DEMOS to take some uncertainty out of my net sand thickness estimations. And then finally, a preliminary King area development plan comparing the possibility of a TLP well or tension leg platform well versus a subsea tieback, and then maybe even an exploration test. Okay, I would like to thank my entire New Orleans team. I'd also like to say thank you to Ed Biegert and Kara Sheik and the entire PFARS team for all their help. I'd like to thank all my professors. Oh, I don't want to cry. Okay, this is serious. Okay. I just want to thank everybody for all their time and their support and their help.
Thank you.
Especially thank you to Dagmar and Emily. Okay, yeah.
Any questions?
Yes.
Kristen, I really enjoyed reading this. Brought back a lot of memories of working in the Mars Basin a dozen years ago. So your reservoir 10 and 11, are those the only reservoirs that were Miocene? Were the other ones Pleistocene to 5 and 6? Because the reason I'm asking this is the amplitude issue. The Pleistocene features in this Mars Basin are what we call a class 3 bright spot. They're bright with normal incidence and they increase in brightness. But the Miocene bright spots here are class 2, and so they're either side of 0 at normal incidence, and they get really bright with offset. So my question had to do with, especially reservoirs 10 and 11, which I suspect are Miocene. How did you get the amplitude features that you were using to initially define what looked to be the boundaries of the reservoir? You said you extracted them, and I was curious as to how that happened.
I just did a very general amplitude extraction, so we can go back to the view of it.
Yeah, like that one there, you showed
So I'm sorry.
that circle. Yeah.
Oh, right here.
Yeah, that's an area of interest. I don't know whether
Yes, so I just did a general interpretation. I was encouraged to take my interpretation as far as possible. So I've mapped pretty much everything up to as close as possible to the salt. So I think that some of this brightness, you can't see it in this particular view, but in some other places, it's particularly bright along the salt. So there's one of two possibilities. It could be that there's a lot of hydrocarbons there, it's being trapped by the salt, or it could be an artifact from the salt. Unfortunately, I didn't have enough time to really explore all of that. It was just, the focus of the project was to really look at the deeper reservoirs and see, is the resolution of this data set going to help us? In cases like this, where it's really discontinuous, not so much.
But so you started with acre of the, you had an acreage, and you turned into acre feet, then proceeded on down.
Yes.
So the initial acreage, though, was some sort of a measure of the reservoir from amplitude, or what?
Yes. So when I did to determine the acreage, so like I showed in this example, I had one with just strictly to the amplitude, and then one going to closure, even though you see that there's really not very many bright areas around it. So that was a comparison that I did when I initially did my assessment. I mapped just to the amplitude. But then sometimes it didn't make a lot of geologic sense. Well, why would it just stop right here? So that was a comparison that I did. I found that it made more sense to follow along closure. So does that answer your question? Or?
Thank you.
Yes. Yes.
What are the advantages? Why did Shell choose to do an ocean bottom study rather than a conventional surface study?
You know, I can't answer that question. I wasn't really involved in any of the processing. I just did the interpretation. So I don't
Okay,
know.
that's all right. I wasn't looking to get.
Are there any other questions? Yeah.
Do you know what your tuning thickness is?
I don't. No, I
Well,
don't.
just a question, because if you've got 23 feet in some of those, the one that you showed, one of the shallower ones, you'd have to have a pretty big, it's really hard to see 23 feet at that depth and really rely on the number being correct. So I'm just curious.
You mean in the seismic data or in the
Well,
log?
In the log, yeah, but to be able to really tie that and then tie it to the seismic and then know that you're exactly right, you have to have some error in there in your sizes, because you really don't know, unless you know exactly what your tuning thickness is, what you can rely on as being accurate.
Right. Yeah, so when I did the sand thickness estimations, I solely used the well log. I didn't rely on anything to do with the seismic.
Thank you.